this college algebra lesson, we're going to talk about variation and its applications. We're going to first talk about direct variation. Direct variation gives rise to a linear function, y is equal to k of x, where it says k is a positive constant. We're also going to say that k can also represent the variation of constant, is another word that you might see it as. We say that we have direct variation, or some other words that you might see that would indicate to use this equation as y varies directly as x. Another key word, y is directly proportional to x. And the k is called the variation constant or the constant of proportionality. So in these equations, they're going to give us some words and in a sentence, and there's going to be some clue context or context clues within here that we need to pick out in order to determine which equation that we're going to use, which is why I underlined varies directly or directly proportional. When I look at example 1, it says find the variation constant. So we first need to find k. So we need to find k. And an equation of variation which y is varying directly as x. So y varies directly as x tells me I need the equation y equals k times x. When it's giving me a value of y and a value of x. Well, if our goal is to find k, I can then use the given y and x values to find k. So 32 is equal to k times 2. When I divide both sides by 2, I get 16 equals x. So the variation of constant is 16. And then we can find the equation of variation by saying y is equal to 16x. Usually at this point, we would have to do something else with it. So our first goal is to find k, create an equation, and then do something else. So that's what we're going to do at the next example here. Water from melting snow. The number of centimeters W of water produced from melting snow varies directly as S. So here's varies directly. That tells me I'm going to use the equation y equals kx. Since W varies as S, we're going to use W as our y value and S as our k value. Or you could still use y and x if you choose. Meteorologists have found that under certain conditions, 150 centimeters of snow will melt in 16.8 centimeters of water. To how many centimeters of water will 200 centimeters of snow melt? So let's first talk about, we have this piece here, 150 centimeters of snow, so that will be our S, is going to melt to 16.8 centimeters of water, which is our W. We first need to find our constant. And then we'll do something with it. If I know that W is 16.8, I can use that for my W value is equal to k times 150, which is our S value. Now we can find by dividing by 150. I see that our variation constant is 0.112. Then we can write our equation of variation. W of S is equal to 0.112s. Now we can answer the last question. How many centimeters of water will 200 centimeters of snow melt? Now I can use this value here as two-step problem. So we first found our constant, then we found our equation, and now we can do something with it. I'm going to plug 200 in where I see S so that I can multiply. Multiplying 200 times our variation constant gives us 22 4/10. Therefore, 200 centimeters of snow will melt to 22 4/10 centimeters of water. Let's look at inverse variation. Notice inverse variation happens when we're dividing, we're not multiplying. Some key words to look at, we have the equation y is equal to k divided by x. So if we see the verbiage inverse variation, y varies inversely as x is inversely proportional, where k is still the constant. K is still the constant. So our first example is keeping it basic. We need to find the variation of constant, so we need to find k. And then our second step is to create an equation of variation, which y varies inversely. So that tells us varies inversely tells us that I'm going to take my constant divided by x. And y is equal to 16 and x is equal to 3/10. So I have my y value, I have my x value. When I multiply by 3/10, I see that k is equal to 4 8/10. So our constant of variation constant is 4.8. And then our equation in step 2, y is equal to our constant 4.8 divided by x. At this point, then we would be able to do something else with this equation, but this is where we can stop. Example 4 here, we're going to do all three processes. The time t, so here's a variable, required to fill a swimming pool varies inversely, so that tells us we're going to divide our k by something as the rate of water. So I'm going to have t is equal to k divided by r. It's asking us that a tank truck can fill a pool in 90 minutes. So this is the time it takes at a fill rate of 1,500 liters per minute. So we also have our r. How long will it take to fill the pool at a rate of 1,800 liters per minute? That will be our third part. So we first need to find what is our constant. Well, I know that my t value is equal to 90 minutes. And I'm just going to get rid of this. This might be confusing for now. So I'm just going to say this is t. And t is 90. Is equal to k. We know it's varying inversely over 1,500, which is the rate. We can get k by itself by multiplying and getting a very large number here. So 90 times 1,500 gives us 135,000. We now have our constant. We can write our equation. So t of r is equal to 135,000 over r. And now we can answer the last part of the question. Now that we have our general equation, we can find how long it will take to fill the pool at a rate of 1,800 liters per minute. So I have a new r that we're going to find. So I want to find t of 1,800, or 135,000 divided by 1,800. When we divide, we get 7.5. So it would take approximately 7.5 minutes to fill the pool at a rate of 1,800 liters per minute. The next part of our notes talks about 3 other different types of variation. Y varies directly as the nth power of x. So here it's telling us that varying directly, we know, means that we're going to vary using multiplication, except this time we're putting a power with our with our x value, and it will tell you what power to use. We can also vary inversely with a power of x, and it will tell us, or y is varying jointly. So jointly means that we're going to multiply it by 2 other items, or 3 other items, or 4 other items. It'll tell us with our constant. right, so example 5. Find an equation of variation in which y varies directly as the square of x. Varies directly, so y is varying directly means multiplication as the square of x. The square of x. When y is 12 and x is 2. So we need to find our general equation. That tells me that we're going to use y is equal to k times x squared. I know y is 12 and x is 2. Taking 2 squared and then dividing each side by 4, k is equal to 3. Putting it back into our general equation then, y is equal to 3x squared. And at this point we could then do something further with it if we had more information. This one just asked us to do a general equation. Find an equation of variation in which y is varying jointly. That tells us that we're going to multiply together then k times x and z. Y is equal to kxz. It's telling us that y is equal to 42 is equal to k times our x value of 2 times our z value of 3. And we're just finding the equation. We're not doing anything else with it. 42 is equal to k times 6. Dividing both sides by 6, we see 7 is equal to k. So our equation of variation is y is equal to 7xz, where then we could potentially do something further if we had more information. Couple more examples. Find any equation of variation in which y is varying jointly. So we know we're going to multiply x and z and inversely. So y is going to vary jointly. So we have k times x times z tells us we're going to vary jointly, multiplying. And then inverse of the square of w. So we can combine inverses and jointly and direct variations, all different kinds of them, by the order in which we read them. It's telling us that y is equal to 105, x is 3, z is 20, and w is 2. And we're just looking for the equation of variation. So we just need to identify what is our k value. So going across, we have y is equal to k times xz, the varies jointly, divided by w squared inverse of the square of w. Plugging our values in, I have 105 is equal to k times 3 times 20, x and z, divided by w squared, so 2 squared. Multiplying, we have 105 is equal to k times 60 over 4. I know that 60 divided by 4 is 15. So when I divide both sides by 15, we have 7 is equal to k. So y is equal to our k value 7 times xz over w squared, or we could put the 7 in the numerator. Either one is fine. The volume of wood V in a tree varies jointly. So V is varying jointly, so that's going to be our y value, as the height and the square of the girth. So we know varying jointly, we're going to multiply two variables together with k, except I'm taking the square of the girth g. So I'm going to take g squared when I multiply them. V is equal to k times h times g squared. And it tells us the girth is the distance around the tree. It's telling us then that if the volume of a redwood tree is 216 meters cubed, when the height is 30 and the girth is 1.5 meters, what is the height of a tree whose volume is 344 meters cubed and whose girth is 1.6 meters? So we first need to find our k value. We need to then find the general equation, and then we can answer the last question. So one of those 3-step pieces. So it's telling us that the volume is 216, our height is 30, and our girth is 1.5. So we'll plug that into our general equation that we determined was our variation equation. 216 is equal to k times our height of 30 times our girth squared, 1.5 squared. Multiplying 1.5 times 1.5 gives us 2 25/100ths. Multiplying that by 30 gives us 67.5. When we divide by 67.5, we find that we end up with our constant at 3 2/10. So now we found our k value, which we can move into our k value to create our equation of variation. Now that we have our equation of variation, we're able to solve for the last piece of the sentence. It's asking us to find the height of a tree whose volume is 344, but whose girth is 1 6/10. Our volume is 344. We know our k value. We do not know h because it's asking us to find the height, is equal times 1 6/10 squared. When I multiply 1 6/10 times 1 6/10 times 3 2/10, we have 8.192. When we divide, since we have a large decimal, we'll probably get a decimal. Anyways, we get approximately 42 meters high. And this concludes our lesson on variation and application.